Joe Armstrong once again, and he will be discussing a more technical problem, specifically the Sherlock Problem, which I have no idea what it is, but we'll find out soon. Joe Armstrong.
Me. I'm Joe Armstrong. Actually, when Garrett first broached this idea, I thought I would talk about the Sherlock Problem, because it interests me, and it was going to be a longer talk. And then I saw who was coming, and I thought I'd give two talks, a sort of history talk and then the Sherlock talk, but I'll trim the Sherlock talk down. So what's the... That's good. So I have to tell you what the Sherlock Problem is. This is a problem that's interested me for many, many years. And in the latest edition, or the second edition of the Erlang book, the last chapter is about Sherlock. And there's one solution to the Sherlock problem. And I was ever so excited about this solution. I thought, oh, it's really cool. And I didn't manage to solve it all. And there's a load of exercises I'd like people to volunteer to help improve the solution. And then I wrote it, and then, you know when you've done some work and you've got it, you've done the last thing, you've written the book, it's all ready, and then you think of a better method. And you, oh my God, there's a much better method. So I've thought of a couple of methods which I think might be better, but I haven't tested them, so this is highly speculative. And what I've noticed is when I program, somebody said to me years ago, he's a very good programmer, I think it was Sever Torstendal said to me, he was the guy who influenced Erlang a lot, and he wrote Eri Pascal, which is a parallel version of Pascal. And he said, you know, how can you be a very efficient programmer? And I said, yeah, how? And he said, by not programming. Right. And just and he said, what you have to do is think about your programs an awful lot before you write them, so that when you get around to writing them, they work. You know, and you've already thought out all the problems. So when I was younger, I used to rush ahead and write programs because I just thought programming was absolutely so much fun. You know, and it does stuff, and you can control this machine, and it's fantastic. And then I found if you practice this for, I don't know, 30 or 40 years, you get sort of reasonable at it. So the sort of making it work challenge for me is sort of gone away a bit, because I write the programs, they work. I mean, they just do what I tell them to do. So it's more challenging to think about what problems you're going to solve. And if you can think them through from right to the start to the complete end, and somewhere along that track you get to, oh, but it wouldn't work, but you don't need to bother to write them, you see, so you save yourself an awful lot of work. So I tend to think about things for a long time. And when I say a long time, I mean 5 to 6 years to 10 years, and then I write the program. So, and I get stuck. So I'm thinking about, like, I've got about 50 problems I'm trying to solve, and I think about them, and I think about them for a few years, and I get stuck, and then I see something in the future, and then I get unstuck, and I think about them a bit more, and then I write them. So the problem I've been thinking about, the main problem I've been thinking about for the last 30 years, I think, is how to organize data, how to organize ideas, how to organize this chaos of fragmentary information we have. And so I try to formalize that in some sense. I've given it lots of names in the past, and it'll have lots of names in the future. And basically, it's a sort of database of ideas. And I'm thinking, really, I started looking up on the net. I was thinking, so you have relational databases and things like that. And then these days, key value stores are very popular. Very sort of trendy, oh, key value stores, yeah, they're great. And I thought, well, can you generalize key value stores? What's the next step after key value stores? And I thought it's just value stores where there's no key, because, I mean, it's always difficult to think of a name, right? So when you have a key value store, you've got to think of the name of the key. So that's a difficult act. What's the key going to be in my database? Oh, that's difficult, I know. Why don't you just have value stores where there are no keys? So I thought, yeah, and I started kind of Googling value stores, and you get like shopping stuff, and you know, you can buy suits cheap and stuff like that, and that didn't help really. So I thought a value store is something we just store values. So I thought, let's just make a database. We only store values. But how do you get stuff out of the database? Ooh, I don't know. I hadn't thought about that. So the problem is, how do you get stuff out of the database? Right. So what's the Sherlock problem? Well, the Sherlock problem is the fundamental problem of research. If we can solve the Sherlock problem, we've solved all problems. Right. So it's a good problem to solve. So here's a formulation of the Sherlock problem. Okay. So there's one X, and there's thousands of Ys. Millions or trillions of Ys. And the Sherlock problem is which I, which I'll call them Y of I, which of the Ys is nearest to X? That's the Sherlock problem. This is the problem all researchers have. What researchers do is they look at data and they notice a similarity between two different things and they can describe that similarity. That's what research is. And why do I want to solve that problem? Well, I want to write things like, if we could solve this problem, we could do some interesting things. So here's some interesting things we could do. I'm writing, word completion. When you're writing a word in a document, no, I thought that's feedback. You start typing a word, and the spelling checker suggests what the completion of that word would be, right? So I was thinking, when you're writing a program, maybe once you've written like 10 lines of code or 15 lines of code and you hit escape, the system will complete the program for you. It'll figure out what you're doing. It'll just write the whole program for you. Right. So what I was thinking is suppose I'm writing a module, let's call it x.erl. On this machine, I've got about 50,000 Erlang modules. I just counted them. I think it's about 50,000. Some of them I've written myself, others, a lot I haven't written myself. They've come from open source projects and things, and they're scattered all over the disk, but I know where they are. And so once I've started writing my code, I've written maybe 20 or 30 lines. At that stage, I want to ask the system, of these 50,000 modules, which is the one that's nearest to what I'm writing? Because if I can find one that's near to it, I might like to look at that code. It might do what I want. And if I were to generalize that and say, well, maybe you've got 50,000 Erlang things, and you've got 50,000 on your machine, and you've got 50. So can I ask the system, okay, not just me, but everybody else, can I find this nearest thing? Okay? And I find that very useful because I work on a lot of different programs. There are a lot of different stages of these programs. If I could find these ones that are near, they would help me a lot. So that's one problem I could solve if I had that. Another problem I have is in fact, this is the one I solved in the book. And I'm not really happy with the answer now. I was happy when I did it, but I'm not happy anymore. No, don't say you're filming that. The book's wonderful, and it's an absolutely brilliant program. But it can be improved slightly. So at the time when I sent the book off to press, there were 73,445 questions that had been asked to the mailing list. And so I was thinking to myself, can I write a program that will help beginners understand their programs or their problems? And I noticed that people ask the same questions over and over again to the mailing list. So I thought, can I write a program that, given a question, let's suppose somebody asks a question, it goes through these 73,000 things and finds the answer that's nearest. Because somebody might have asked a question that's something like that. So can I do that? And I'm going to show you the solution to that. That's quite interesting, because what I do there is I have an algorithm there that, given a question, will find the nearest question using some definition of nearest. And it goes through them all, and then it prints them out, and you can look at them. And then you can choose one of those and say, yeah, that's almost an answer. And then I can do it recursively and say, well, what's the nearest answer to that answer? And I can filter them by date and time and person and who answered and so on. So I thought that's a useful program. There's another problem with files and things. I often get just when I'm working, I get little ideas, and I want to tell the computer. I still think a notepad, I carry a notepad around, I still think a notepad and a bit of paper in my pocket with a pen is actually much better than a computer. I would like computers to be as good as that. You just sort of jot them down on a bit of paper. You can't just... If you just jot an idea down on a computer, well, how do you find it later? So let's suppose, let's do a little thought experiment. You write a little thing. You open up Emacs or something, and you write a little idea that's 100 words, and you want to store it somewhere. You've got now an enormous problem where you've got to choose two things, right? You have to choose a file name, and you have to choose a directory to put it in. And both of those are... You remember I said choosing names is difficult? I've given you two very difficult problems. This is the categorization problem. The categorization problem is extremely difficult. If I once built a a file system in my office, and my office is full of papers, and I thought, oh, I know, I'll organize everything. And so I got a lot of files out of the stores, and I put labels on them, on the backs, and one said correspondence, and the other said lecture notes, and the other said papers, and the other said this, and then I took all these papers, and I started going, what do I put this on? It's a letter. Okay, put it in correspondence. Hang on, this is a letter about a conference. Does it go in conferences or does it go in letters? I didn't know. You see, this is the categorization problem. As soon as you put categories onto things, you don't know what category. And this is the problem in object-oriented programming. This is why object-oriented programming is bloody stupid. Okay? Because it asks you to... No, you see, there's a great difference. Object-oriented programming asks you to put things into categories, into classes. Right. Concurrency-oriented programming asks you to identify the concurrency in the problem. Now, the concurrency in the problem is a property of the real world if you're doing real-world modeling. And you can see it, you can smell it, you can eat it. What's the concurrency model of this room? It's the number of people in the room. It's 56 people, if there are 56, you know. If you're modeling lifts and things, if there are 3 lifts, you can have 3 processes. You're not going to have 4, 16, 12, or 32. You're going to have exactly 3. So this is what Carl Hewitt calls physical modeling, because I'm an ex-physicist. You look for the concurrency that's there and you model it. So I have no problem with that. But I do have a problem with the categorization problem, because I cannot say this thing's got to be in that module or that class. Okay. So here's the problem. I've got this little file, this little fragment of information. I want to store it somewhere. And I want to build on information that I've already done before. So what I want to say is, okay, in my value store, which is just values, when I want to store some data, find me the value that is nearest to the new value. And it might turn out that the old value is actually very similar to the new idea. In that case, what I want to do is merge the two and add to the old idea. Because I've just dropped my ideas down. And it's even worse. I have like... I don't know, a dozen computers I use, and I don't know which machine I put them on, and every time I bought every time I bought a new machine, I've just transferred the entire file system of the old machine onto the new machine, and I just can't find anything. I mean, it's a complete mess. Right, so I want to solve that problem. So in order to solve this, we need some notion of similarity, because I want to find the most similar thing. So here's 3 notions of similarity. The first one is called TFIDF, similarity, and that's the one in the book. Okay, so, and that was the one I thought was pretty good. The 2 that I now think possibly better, one is naive Bayesian, and the other is, I'm going to leave it as a surprise to the end, okay? Because it turns out to be extremely simple. And this is like, you're really pissed off. Oh, why did I discover that? And I discovered it actually by reading some papers on machine learning. Okay. So just quickly go through this, because it's not going to be a long talk, and there's not going to be no code or anything. So TFIDF, does anybody know? Has anybody heard of that? It's called term frequency times inverse document frequency, and it's based on a very simple idea. If you've got a document, a document's this little fragment I've written. You want to characterize that document with keywords. That's going to help you a lot in understanding it, because the categorization into keywords is the class or the category. But let's do that automatically. Okay, so how do we discover what words should be keywords? What we do is we compare the frequency. There's something called the corpus. The corpus is all documents. So you work out the frequency of the word in the corpus, and you work out the frequency of the word in the document. And if the 2 are radically different, or rather in the document, if it's much greater than in the corpus, it's significant in that document. So if I've got a word like cat, or dog or something, take the word cat, and in the corpus it occurs in 2% of all documents, but in this particular document it occurs 10% of the time, then for that document it's very significant. So that's a very simple idea, and it's called the term frequency. If the term frequency is how often it occurs in your document, the inverse document frequency is 1 over the log of the number of times it occurs in the corpus. Right. And so there's just the description. That's from Programming Erlang version 2, volume 2, 2nd edition, which is a wonderful... all right. I won't come here and talk again. And it's on page 468 of Programming Erlang 2nd edition. So that algorithm is described there. So what you do is you trundle... What I've written is a program that does the following. you screen scrape the Erlang mailing list. So this is a Piper mail list. It's done in the Piper mail format, and it's on erlang.org. So I've written a little program. I think it uses Cowboy or something, and it just goes, fetches the pages, and that contains the indexes. And then that points you to mail in the Piper mail format, and then I parse them to extract all the mail. And then I compute the keywords in everything. And it's not only keywords, you get a probability from this, that it's a significant word. And then I choose the 20 most common words, or the 20 most probable keywords for each document with the probability that it's a keyword. And I store that together with the document. And that takes a while. It doesn't take that long, it takes about 5 minutes. And then when I give a query, you take the entire query, compute its keywords, and then compute what's called the cosine similarity of these two sets. So these are two sets of keywords times probability. So keywords and probability, you multiply them two together, and that gives you the significance of the document. Then you do that for all documents and sort it, and look at it. And it works quite well, because the first test, I downloaded all the Erlang mailing lists, and the first thing I did is I typed in 3 lines about TFIDF similarity, and it immediately found 3 postings on TFIDF similarity measures, which were made by complete strangers to me years ago. And then I recursively searched them, and it found a load of references that were interesting. So I was very pleased about that. So choose the best. So that's the algorithm in the book. Very happy about that. Right. So what didn't it have? Well, it didn't have a nice user interface. It's just a command line interface. So I've set as exercises, if anybody likes to do it, make a web interface to this, sort of integrate it and do it. And I think actually it'd be a good program to write, because I think there's a lot of forums out there, and they contain an awful lot of information. So in any technical subject, any non-technical subject, there are forums, bulletin boards that have been running for 10 years. There are tens of thousands to hundreds of thousands of postings in these forums. So if you did a bit of screen scraping, extracted all this information, put it into a form where you could search it easily, you might find out all sorts of interesting information. This is a much better way of searching than Google uses. What Google does is when you Google something, you have to think up the keywords that will characterize a document. You write a sentence here and you hit search. And you may or may not find the documents you're interested in, depending upon whether you've chosen the correct words. If you've chosen the correct words, you find decent document. If you've chosen incorrect words, crap. Okay? This doesn't do this. It says, okay, I've got this document. This is not 1 or 2 words. I don't know which words to use as keywords. I'll just use the whole document as a search term and find the most similar document. So I think it's cool. Right. So we've got no nice interface and anything and anything. Anyway, so I thought, and that, when I wrote that and I was pleased with it, and it's a bit slow, and I thought, well, we can pick it up and make it nice. And then I began to think, I taken a course on machine learning, and just for fun, and came across some other ideas. The first one was naive Bayesian. Excuse me, you know Bayes' law. It says that the probability of A, given that B's occurred, times the probability of B, is the same as the probability of B, given that A's occurred, times the probability of A. And why is that? I mean, that's very simple to understand. If you look at this, what is this? This first term, probability of A times the probability that B has occurred. Sorry, here's the probability of A occurring. Given that A has occurred, this is the probability of B occurs. So that's the probability of A and B occurring. It's also, but the probability of B and A occurring is the same as the probability of A and B occurring. Okay, so you could just equate the two. But you normally see it in a different form. You normally see it in this form. So it says the probability of A given B is the same as the probability of B given A times P of A divided by P of B. So it's standard statistics. And it's very useful. I'll give an example. I find it a lovely example. Because most people don't understand Bayesian logic. Right, okay, so here's an example. Suppose you're looking for a restaurant. The probability that, and assume that the probability that a restaurant is bad is 1/3. Okay, that's P of B. P of B is the probability of a bad restaurant. Assume now that restaurants make mistakes printing their menus. Okay, So a good restaurant's going to take care printing its menu. A bad restaurant is going to print smudgy menus, right? So let's have some conditional probabilities. Let's say that the probability of a smudged menu, given that it's a bad restaurant, is 3/4. Bad restaurants don't take care with their menus. They're smudgy things. Let's say the probability of a menu being smudged, if it's a good restaurant, is 1/2. Because that's what we know. And now, let's imagine we're going out in the evening, and we want to find a restaurant. And we walk down the street, and we see a menu, and it's smudged. Right. So we ask the question, what is the probability that it's a good or bad restaurant? Because now we've got more information. So what I want to know is, this is what I've seen. I want to know, this is what I'm after. I want to know the probability of it being bad, given that it's smudged. But you see, I don't have this. I don't have B given S. I've got S given B. I've got the opposite up there. That's what I know. So I apply Bayes' formula. Bayes' formula says that given these probabilities in that order, I can work out the inverse. So it's just that times that. It's probability of smudged given bad times probability of bad divided probability of it being smudged. And what's that? Just plug in the numbers. And so if you see a smudged menu, then you can deduce from Bayes' rule that the probability that it's bad is 0.43. It's not 0.433. It has modified the probability. Okay, so that's an example of Bayes' rule. It actually comes from, I can't remember the name of the bloke, but I didn't think of that. This is from Andrew something or other at some university. Somebody put me right there. Well, never mind. Right. So we can apply this. Let's suppose we want to categorize a tweet. So here's tweets about cats. Well, there have only been 4 tweets. This is Twitter. And here we are. These are the names. These are the names of Tizzer's a made-up name, actually. Tubby and Tiger are both unfortunately dead. They were cats I had a few years ago. And Nemo is a cat that my daughter has. And I don't have any dogs, but dogs are always called Fido and Rover. In Britain, I don't know what they're called in America. Are they called Fido and Rover here? Oh, good. So here we are. We can write down these conditional probabilities. The probability that we've got the hashtag dog, given that it's Fido. But what do? We take all the things that are Fido and divide by, we take all the tweets that have got the hashtag dog, and we divide by all of those which have got Fido. So it's 2 out of 4, because 4 of them there are 4 Fidos. Wait a moment, no, yes. I got that wrong. Why is it 2 over 4? Oh, there's 4. Oh, there's 4. Oh, I don't know. Maybe I've got it wrong. You can think it out yourself. Might not be right. But basically you've got this. Given the hashtag cat, what's the probability that it's a Fido? Given that it's a given the hashtag, you know the probability of that word. Okay, so now you've got a tweet that doesn't have any hashtags in. Which hashtag should I add to it? Because the hashtag I add to it, that's a category. Okay. So all I've got to do is invert the Bayesian rule, work out the probabilities, and the one that's maximal is the hashtags that thing should have. So it's worked out the categories for me, which is quite nice, because that's the problem I want to have. I just write my information, but I don't know where to store it. Okay, I'm going to store it with hashtags something. I don't know what they're going to be. So let's compute this, and that's Bayesian, naive Bayesian. And it's said to work pretty well. If you compare, you can do experiments with naive Bayesian. So how do you do an experiment? You add the hashtags to there, and you remove them. And then you perform the experiment, and then you see how often it was right. And it's right in about 75% of the time. So it's a naive Bayesian, it's pretty good. And so that's one of the experiments I think I'll do. Well, no, I'm not going to do it next, because there's a better method. So, is there a better method? The answer to that is going to be, can anybody think of a better method? Or perhaps you just know. Right. So it is the simplest, once somebody's pointed it out to you, it is the simplest thing in the world. It is so beautiful, it is so fantastic, it's so easy to implement. It's called normalized compression difference. And it's based on this very, 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 very simple idea. Suppose you've got a file A, and you compress it, you get a certain size. Now suppose you concatenate A with A and compress it. How big is the compressed size of the two files concatenated? It's going to be almost the same as A with a little bit extra. Because that's what compression means. It means find the similarities between the two things and describe that difference. That's what compression is. If you take LZSS algorithm, it actually has a pointer into the old stuff and then a length count. That's how it works. So if you've got A followed by A, first of all you compress it. The second A is just going to be a pointer into the old A and a length count. So it compresses beautifully. This method is extremely insensitive to the compression algorithm. In fact, it works better with better compression algorithms, but you're not going to use it for that. You're going to use it for ranking. And so the ranking doesn't change as you change the compression algorithm. It's very insensitive to that. So all you do is you compute. You've got your file A, this is my X, and then you compute A plus B, and you work out, you compress it. But you want to normalize it, so you divide by the max of the size of A compressed or B compressed, whichever happens to be the bigger. And that's the normalized compression distance. And there's none of this mucking around, sort of building tables and everything. Okay, you've got to do compression quickly, but that's not a problem. So I think that might be I'm going to do that and see what happens. So the next time I want to find some code, I'll just write a bit of code, compute the normalized compression difference over all the files in my module, just sort of indicate that, and then just start looking and see how good it's doing. And then I'd like to build another thing, which is I've had in the back of my mind for several years, and that's I'd like to build an IDE. I don't like the fact that programmers are isolated. I hate all these Git and all this rubbish stuff. I mean, it's horrible because it makes you think that programmers are individuals and not part of a community. It makes them think that what they're doing is isolated. This whole model of it's saying, okay, we're not going to. You get late discovery of the fact that somebody else is doing the same thing, and I don't like that. I want early discovery of that fact. And so I was imagining a kind of social programming network, rather like IRC. So it struck me that in Erlang it'd be pretty easy to write. I haven't written it. Somebody here can write it because it's a fun program. You start writing your program in a window here, and of course, after you've written a few tens of lines of code, you've written 50 lines of code, you will know which modules and functions you're calling. That's really easy. You just analyze that code and say, I'm calling the following modules. Right. Then you go out and then you broadcast that to a server somewhere. Right. And then if there are a lot of people programming, they could be programming in Erlang or Java, or it doesn't matter what language you're using. You could discover the fact that somebody else who you don't know is also using exactly the same modules at exactly the same point in time that you are doing it. So in your little sidebar here, the names of people who are also using the same modules will pop up. These are the people you want to ask questions to about your code because it's in their cache. They're thinking about this now. And they're online and they're doing stuff. So we could turn this programming that we do as an individual act into a social act where we communicate with people. And we can use algorithms like this to discover those people and to find the similarities. And that, I think, would be really good, because when I write code, I always think, somebody else must have written this before me, and I can't find it. Why do we write code? Because we can't find it with Google, right? And if we really can't find it, then we can write the code. But, I mean, there's a lot of code you write. It's a pain in the arse. I mean, it's just boring stuff, So that's all. Was there any more? Oh, yeah, well, that was the thing. Right, so that's the Sherlock problem, actually. And I just hope, just giving this talk would stimulate somebody. Somebody here might be sitting in the audience and think, oh, that's a cool problem, and work on that a bit, and work with me a little bit, and try and do something on that. I just think it's the fundamental problem. It's the most fundamental problem there is of okay, I've got this data, but somebody else somewhere must have something that's pretty similar. Where are they? Let's try and find them. The trouble with their algorithms, if you think about them, they're intrinsically horrible. To compute that for all fragments of when this is trillions of things, is a big computational problem. I don't really see any. The keyword thing actually reduces the search space, but it's not a very big reduction. It's only a factor 10 or so. Mind you, computers are getting faster, so we've got to use all these CPU cycles for something, so it might as well use them for something useful. Oh, that's it. Okay. Thank you. And then if there's like questions or something, or you just want to have a beer, or anybody, yeah. Questions and answers, or no, you're brain dead now. Bloke's been talking all evening, we couldn't have a drink. Oh, go ahead. Yeah.
So how does computing the difference of compressed file sizes help you identify what the content of?
Oh no, it just identify with the ones that are similar. It doesn't help me with keywords or anything like that.
They have all the same rules, theoretically.
I don't know, I haven't tried it. But I mean, okay, so if you find the most similar file, then look at the keywords in that file. If it's got hashtags in, we'll use them.
So you still have to look at like what's in each of these files that are similarly sized.
Yeah, you'll have to look at them afterwards, yes. Yeah, sure.
But it just helps narrow down
Yeah.
the result set.
Yes.
Okay. That makes sense.
But it's just so kind of generic. It just doesn't make any assumptions. I mean, compression doesn't make any assumptions at all about the data. It's just, so it's rather nice. Otherwise, you have to make assumptions about the data and analyze it. So the problem with, like, keyword analysis is, first of all, you need a lexical phase to decide what a word is. And that's not a language-independent thing. That depends upon language. And it's actually quite difficult to distinguish sort of real words from rubbish words. So you need a spelling checker or a big dictionary or something like that.
By the way, React can be a value store. You don't have to supply a key, but of course you'll never find anything.
Yeah, well, yeah, but I need to find the stuff, you know. Oh, put it all into React. Oh, yes, right, great. How'd you get it out? We can't. Hey, you could sell a database like that, a sort of write once, read never data store, you know, which can take an infinite amount of data and sell it to suckers for...
Who cares about reading?
Right. Yes. No, that was great. That was good. So, pull that one out. Pull that out.
So as advertised, we also have a completely open question for Joe. Any historical context, any extremely embarrassing and revealing questions, just ask that, and Joe is forced to answer them by fiat. Yeah, it's almost a game show type of thing. Now,
so if there's one or two things that you wish you hadn't done in Erlang at the very beginning that sort of lived through the lifespan of it that you're dealing with now, what would they be?
Oh, macros and include files should be removed. They're horrible. Strings are okay. There are some widely held and incorrect views about strings. But the macros are a pain. There's not stuff that's in that I don't like, but there's a lot of stuff that's not in that I would like. But it's very difficult to put new stuff in. And a lot of stuff isn't in because, I mean, if you do it again today, it wouldn't be done like that. And it was because of the sort of memory requirements and things like that. For example, you can have two versions of a module, an old and a new version, and then you have to purge the old one before you can put a new one in. But in fact, with the amount of memory you got today, you could have multiple versions and garbage collect the ones that are not being used. So you could just carry on forever, really, and things like that, which you would actually be different today. And so one problem with Alexa is going to inherit those bad things, you see. So really it needs a new VM to do that as well, or tweaking it. But that'll come. We could do that. Maybe the atom table should be garbage collected and sort of things like that.
Robert should be here for that, right?
Yeah,
Fair enough.
well, whatever.
Right?
You know, I mean, we don't.
Robert should be here for that. What?
So what did finally convince Ericsson to open source it?
There's a camera rolling. Now, when the camera's off...
Turn the camera off.
No, well, the brilliance of our convincing arguments, of course. No blackmail, no. We just argued the case so well.
I'm going to ask a question if you don't. Okay. And no one wants that.
So back to the compression algorithm that you were talking about, how do you take into account things that are named differently? Structurally, the document might be similar. So if you're talking about two programming modules or two Erlang modules, and they are functionally and structurally similar, but they have completely different names.
Yes, I don't know. I haven't a clue. I mean, subject to an isomorphic transformation. Yes. That would be a very smart compression algorithm that would realize that those actually are two pretty similar if we renamed everything in a consistent way. But I don't know if there are compression algorithms like that.
I think you'd have to operate at the abstract.
Yeah, it would be, yes. Yes.
You have to know that it's a program.
Sure. Right. So how do our brains do that? You look at that code, and you look at that code, and you say, hang on, they're actually the same. But the variable names are all different, the structure is slightly different, and you think, that's the same. How do our brains do it? I don't know. I don't know.
So
I'd love to know. It'd be fantastic.
I have a question. There's your languages. I'm just going to throw them out there. Clojure, Scala, Node. They seem to be sort of new on the stage here. Kind of new upcoming languages. Is there any sort of competitive impulse in you to say, stop, or wait, or hang on, or like, let's talk about this? What would you say? What's the topic with respect to these new upcoming JVM or async, quote unquote? What do you say to that?
Well, yeah, they're okay. But I think looking at, Phil Wadler asked me if I could participate in the design of a new programming language. And I said no, because I didn't think it was very interesting. Because I thought that they're looking at the wrong problem. Because, Peter Landin wrote this paper, The Next 800 Programming Languages, and there must be 800, thousands of programming languages. And so people are like inventing new programming languages all the time. But I think that's not the big problem, is actually writing programs. I think the big technical problem in building systems is what I call the connecting things together problem. It's a version nightmare problem. It's given things in different languages and so on. It's actually connecting them together. So I am very much into, if I want to make a language, I wouldn't make a programming language. I would make a protocol description language where you can formally describe protocols, formally, and you can formally validate that the components are obeying the protocol. And I would put these between everything that communicates in the form of a contract, and I would like to throw contract violations. I do not think we can build systems that are large with large components. I think that somewhere between 64 kilobytes, I think the entire, for those of you in my lecture, I showed, my view of the world. I don't think a computer or a program should be bigger than possibly 128 kilobytes, possibly 64 kilobytes. It should be possible to understand that program in its entirety. And I don't think if you put more than like 64 kilobytes of code into a processor that anybody can understand it. So I think we have to think about how can we make systems out of very small components with very strictly defined protocols between them. And I think we need to start describing configuration languages that describe how the thing is built and configured, protocol description languages that describe how the protocols work. And I don't think how they work to me, programs are black boxes. There are two levels of abstraction. You've got the black box abstraction. One of the most important things in computer science is the principle of observational equivalence. It says that two programs are equivalent if you cannot distinguish them by looking at their inputs and outputs. It's a very important principle. It's in CSP and things like that. So to me, a program, it's a black box. You send a message in, you get a message out. I don't care if it's written in Scala or Haskell or Erlang or Python or Ruby. I care about this relationship between the inputs and outputs. And so at a higher level of abstraction, we're not interested in how it works internally, which is why I say I'm not so sort of wound up about how it works or about the program, but I'm extremely wound up about how we describe what's going in and out. Now, most people think a protocol description language means describing the individual packets, but not the order or the semantics, not the ordering of them. So APIs in programming languages are completely stupid because they do not capture order. So, for example, in a C program or any programming language, you've got an API and it says, if you open a file, you get a file handle back. Given the file handle, you can read and write the file, and you can close the file. But a program that says open file, close file, you've got the handle, read is a legal program. And it will type check, and it's correct. So this API that says open a file, you get a file handle back, read a file with a file handle, you get the data, close the file with a file handle. Wait a moment, it doesn't say that you've destroyed the file handle when you close it and you can't use it again later. So the APIs we use in programming languages are not adequate for describing the order in which we can perform the API calls. So they're basically useless. Right. But we could make programming languages to describe that. I mean, I made a language to describe that. It's called UBF, and it hasn't. And I thought that's got a few sort of fans, and it's if you search for J. Armstrong UBF, you'll find it, and it's just, it's good. I'm pleased I did that. But most problems aren't difficult enough to warrant it. But I think we were going to get...
What does UBF stand for?
Sorry?
What does UBF
Universal
stand
Binary
for?
Format, or Universal Ubiquitous. I can't remember, actually. I think it's Universal Binary Format. It's like all the good things in XML, and it's like XML only far better, and it's like JSON, it's like XML schemas, and XML, and CSP, sort of in a practical format, which is ever so nice. Try it, you'll love it, But I've never marketed it at all. I just wrote paper and hoped that people would find it. Sorry?
But you said earlier that papers never get indexed and never get used.
Well, yeah, but I mean, then I didn't not very good at promoting things, so.
You just got to compress them.
Yes, I'd love to see programming languages that describe protocols, but not that describe algorithms, because there's loads of them. Of course, I'm not against them. No.
Yes.
Oh, yes. Oh.
Just ask you the question. So first, Eric Myers actually talked about a lot of the same things that you were discussing in terms of defining protocols and ways to communicate between software. But the real question is...
Yes. Okay, so the question I'd like to ask, if there's any language that's the extreme opposite end of the spectrum from Erlang in terms of syntax, semantics, and just about everything else, it would be C++, because it's everything that you could possibly throw into a programming language exists somewhere in C++. Do you think if you sat in a quiet room with Strustrup, do you think there's any way in the world you could persuade him that he took a completely wrong path and that Erlang is the model he should have followed?
Well, in a funny sense, he didn't take that. I mean, I have sat in a quiet room with him, but we got on quite well, actually. And he told me that C++ had also been banned on several occasions, so we had a bit in common. No, but I mean, C++, if you're going to do graphics programming or something like that, you need performance and things, then it's a great language, I mean, no language can get to be used an awful lot if it's not a great language. And as Sirstrup said, no, but I mean, one of his quotes, he said, there are two types of languages. There are languages that people bitch about, and there are languages that nobody uses. So no, I mean, but I think the point about programming languages, you should have kind of a realization of which language is good for solving which problem, because we don't like solve all problems using the same programming language. We glue stuff together written in several languages. It's good to have a realization of what's good for what. And it's doing everybody a disservice to say, Erlang's good for compression algorithms or cryptography or something. If it's not, it's useless. I mean, you should do it in C.
If I'm writing software right now, today,
Yeah.
right, I'm making a living. It's a good living. It's fun. It's interesting. What should I be thinking about for the next 5 years? Not 10. 5. What's 5 years out?
What's 5 years from now?
2018.
Yeah, 2018. Yeah. I don't know. I don't know about software. I'm more like think about hardware, what changes that's going to cause. I give several lectures, and one of them is, it's funny, somebody asked me to predict the future a bit, and I gave this lecture, and then a few years later they asked me to come back because everything I'd said had come true, and I thought, I suppose it's because I'm a bit older and I've got these grey hairs, so I see this stuff over a slightly longer time perspective. So the interesting thing that's happening in hardware are what I call scale changes. A scale change is a factor of 1,000, right? Moore's law is saying, say, hardware capacity, memory capacity is doubling every 18 months. Okay, so it takes roughly 10 doubling periods to 10 doubling periods is 1,024. So that's the scale change, and that's taking about 10 years, right? So a scale change in hardware takes 10 years, and if you double the performance of something or double the size of something, not much happens actually. But when it's gone up by a factor of 1,000, you get the scale change occurring. Now, scale changes cause a totally new application you never thought of before. So the place where the most scale changes have had impact has been in memory, right? So when you had the scale change that was caused by the change from a killer to a megabyte of memory, nothing really happened then. It wasn't enough. But the scale change that happened from a megabyte to a gigabyte is enormous because it enabled two basic technologies. I mean, it enabled digital music and digital photography. So my first laptop had a disk of, I think it was 20 megabytes. Right. Now, an MP3 file of music is like 5 megabytes. So on 20 megabytes of disk, I could have stored 3 songs, right? And it was also weighed about 15 kilos. So a 15 kilo thing that can store 3 songs it's not going to make a Walkman or a digital music thing. But when you get to a gigabyte, then you can store 250 songs on it, or you can store 1,000 digital images. So this change from a megabyte to a gigabyte, the gigabyte of flash has caused digital music and digital photography. Right. Now we're going to go pretty predictably into a terabyte of flash within about 5 years. We will see a terabyte of flash in mobile phones within 5 years. The terabyte boundary is going to cause movies to have the same status as films and digital books and things like that. I think every other one is interesting, because I said the 1,000 to the giga wasn't that, but the difference between the mega and the giga is enormous. So the next scale change is a petabyte. That's going to happen within about, I would say, 12 years or so it'll start. That is enormously interesting, the petabyte change, because what's going to happen is all human knowledge, every book, Google is scanning all books. All books that have ever been written will fit into 138 terabytes of memory. That will mean that the petabyte of memory can store all human knowledge, and we can give it to every person on the planet in 15 years' time. And if we do that, it's totally going to change society. As Sussman said, there isn't going to be any work in a few years' time. We can change all, of course there's going to be the physical work of producing food and things like that. And that's what we've still got to do. But all these things are going to vanish. And that's going to happen in the next 15 years. So the social changes that will cause will be enormous. Sorry. There's a hand waving to disagree with me.
The politics of what you're saying is very deep. And everything you've said has a deep political implication, which you've elided.
Yes.
So when you walk down the street and you come across a map, and on the map it says, you are here.
Yes.
When the technology expands, as we've seen it expand, when memory capacity expands, as we've seen it expand, when the ability to capture you there is now available, the problem becomes different. Yes, I think it's true that it is computable to satisfy human needs in a meaningful sense, but that doesn't mean the opportunity to actually engage in those computations for those purposes is open to realization without significant political
No,
consequences.
it will cause significant political change, of
Okay,
course.
so what is your view with regard to political evolution in the context of technology over the next 5 or 10, 15 years?
I don't know. I think we will see repressive states that try and stop technology, and we will find free states that try and promote it. And I think, you know, when I was a kid, I used to read Sussman was asked the same question. And he said, you know, ancient Rome had slaves and things like that. And now we've invented these computers. They are our slaves. He said, I thought it was quite good, I have no problem enslaving a computer and getting it to do my will. And I have no problem with more free time. The problem the problem is providing resources for people. It's not work. It's food and things to do, you know. So things like cultural activities, the problem is the distribution of resources. And I think you're going to go to a model where, I mean, I find it totally absurd that the word intellectual and property, those two things can be put into the same sentence, and you've connected intellectual property with property as if an idea can be owned, and as if you can get money for it. It's not physical. Physical things you can own. You can't own ideas. Intellectual property is ideas. It's passages of noughts and ones. It's totally absurd that you can own these things. And I don't accept this. And I think the computer scientists are kind of in this forefront of people who understand this stuff. You know, we're the slave. I mean, we're not the super rich venture capitalists making all the money out of the technology. We're the slaves who work for them, right? But we have the power. They don't have the power. They can't control the internet. So all these kind of, you know, when the Occupy movement was there with its mobile phones, live streaming, and they were chanting, "The world is watching," and the police is standing off. Do you think they'd have gone in with their batons and things if they hadn't been live streaming it? Yeah, sure they would. Yeah. So, Julian Assange said sort of last week, you know, cryptography was the key thing to put in the hands of the people. Okay, the computer scientists know that. Right, so this is one of the things you've got to do, is make cryptography available to everybody. And the other thing you've got to do is take the data out of the cloud and put it into your home cloud. Make your own home clouds. This is one of the projects I'm doing. I've got a Raspberry Pi at home, and the next thing I want to do is build a proper cloud on it. And I want all this. I want this. I take a photo of my phone, and it goes onto my home cloud, and my friends get it. Fine, that's great. But I want to say who my friends are, and I want it to be encrypted so nobody else apart from who I have said gets that data. And I'm really pissed off if I don't want to go into when I go into a coffee bar in Stockholm and somebody takes my photo, or somebody takes a photo of the coffee bar, goes onto Facebook or something, the bloody thing face recognizes everybody and geotags them. If the NSA will kill Google and Facebook. Sweden has already banned the use of Google in public authorities because of privacy reasons. They're not allowed to use Google, right? It's not widely publicized because they don't like to widely publicize stuff like that. Google apps are not allowed to be used by Swedish authorities. That can kill Google. It can kill Facebook. So there is actually commercial pressure to stop these things. But I think ultimately you've got to take control of your own data. And if you look in Sweden, in the under 30s age group, the Pirate Party is the leading political party. And so as that democratic moves up in age, you know, the Swedish mainstream political parties will not take issue on things like file sharing or anything because they're out to lose. Every time they do it in the courts, they lose 5% of the vote in the under 30s demographic. And we've got 2 European Parliament members in the Pirate Party. So these are the guys saying, and the Pirate Party is smudged by the media, mainstream media, and said, oh, these are a load of anarchists. But in fact, they're the ones who want privacy. They're the ones who realize the dangers of... And all this about, like, oh, we don't store your data, we store your metadata. Well, and I'm not Jewish or anything, but if I was Jewish and there was a Holocaust, you could just kill everybody. You know, I mean, it's amazingly dangerous. In the wrong hands. In the right hands, it's amazingly dangerous anyway, because the next hands might be the wrong hands. You can't pass it on to the next lot. So. But I mean, who doesn't think that? Who's a computer scientist and one of these slaves who works for these big companies? I mean, sorry, that wasn't really about politics. It's about programming. But, yeah.
Not quite political, but one thing I've been curious about with the actor model in Erlang, was that originally part of the design when you first created it, or did it just sort of emerge?
No, I don't think I knew about the actor model at the time. No, I mean,
you mentioned input and output.
Yeah, I mean, it happens to be pretty much the same. So.
Okay.
Ladies and gentlemen, Joe Armstrong. So